made this little video in order to describe as simply as I can the idea of false discovery rate and its relationship to p-values. These are things which are not perhaps as well known as they should be, but they are absolutely essential in order to understand properly how to interpret a test of significance. Neglect of them has probably led to the high irreproducibility problem which we have heard a lot about recently. In order to understand it properly, you'll have to read the paper, but here's a little introduction. Okay, so what exactly is the false discovery rate and what is a p-value? What's the difference between them? P-values are absolutely universal in the biomedical literature and much other as well. Every paper you open has claims that a result is significant or not significant, and it's backed up with a p-value. Very foolishly, people often say something is significant if p is less than 0.05, but the trouble with that is that it doesn't answer the question that you want to know. What you want to know is the false discovery rate, and that is the fraction of tests which come out positive with p less than a predetermined significance level, the fraction that are positive when there is no real effect there, the fraction of false discoveries. That's what we need to know, and this talk is about how to get at it. So let's go over the definitions. The false discovery rate is the fraction of all positive tests that are false positives. In other words, they're tests that come out as, quote, significant, unquote, when the results are all just random variability and there's no real effect. That's what you need to know, and that's what prevents you from making a fool of yourself by claiming that there's a real effect when there isn't one. But the p-value tells you nothing about the false discovery rate. So what is the p-value? The p-value, the definition is slightly circuitous, I suppose, and it's very uncommon for people to be able to recite it accurately when you ask them. It needs a subjunctive tense. If there were actually no effect, if, for example, the difference between two means was 0, then the probability of observing a value for the difference between means which was equal to or greater than the one you actually see would be p equals 0.05, or whatever p comes out to be. A shortcut version of that, which is somewhat misleading, is to say that there's a 5% chance of seeing a difference at least as big as we have done by chance alone. By chance alone, we mean that there's a 5% chance of seeing a difference at least as big as we have done if there were no real effect. You might at first sight think that that means that the false discovery rate is 5%, but it doesn't. And the neglect of the fact that it doesn't is possibly a cause of much of the irreproducibility which has become a great topic of conversation recently. The simplest way I've seen of saying briefly why the p-value doesn't give you a false discovery rate is to paraphrase American statisticians who said, knowing that the data are rare when there is no true difference, that's what the p-value gives you, is of little use unless one determines whether or not they are also rare when there is a true difference. To anticipate the conclusion will be, if we observe a p-value close to 0.05 and conclude that we have discovered something, there is at least a 30% chance of that being a false positive, and that we therefore make a fool of ourselves by claiming we've made a discovery when we haven't. I think the easiest way to explain why it is that the false positive rate is not the same thing as a p-value is by an analogy, and the analogy is with screening tests. Screening tests are a topic of hot discussion at the moment because the government keeps on saying we should do them, but in fact they very rarely work very well, and this is why they don't work well. Suppose that we screen 10,000 people, and suppose that of those 10,000 people, 1% actually have the condition which we're interested in detecting. So 100 people have the condition and 9,900 do not. 1% might be the prevalence of mild cognitive impairment in the entire population. Mild cognitive impairment may or may not lead to dementia, but that's another question. So 100 people have mild cognitive impairment, 9,900 don't. We want to apply a test in order to detect which people have it. Now suppose the specificity of our test is 95%. What specificity means is that if people don't have the condition, then 95% of the people will show up correctly negative, but 5% will show up positive, so we have 5% of false positive tests in these people who do not have the condition. So 5% though is not the false discovery rate, because what we want to know is the proportion of positive tests which give you a false positive, and for that we need to know the total number of positive tests, and to work out that we need to look not only at this lower arm of the tree diagram but also at the upper arm. What happens among the 100 people who do actually have the condition? Well, let's suppose that the sensitivity of the screening test is 0.8. What that means is that you will detect correctly 80% of the people who have the condition. The corollary of that is that you will fail to detect 20% of the people who have the condition. So this gives you 80% of positive tests, and these ones are all true positives because the people actually have the condition. The total number of positive tests is therefore 495 false positives and 80 true positives. So the proportion of positive tests that are false is 495 over 495 plus 80, which is 86%, not 5%. When someone tests positive, there's an 86% chance that they haven't actually got the condition, only near 14% chance that they have got it. So the test is absolutely useless. Now let's extend this to the problem of significance tests. Let's suppose we test a whole lot of drugs one at a time. Over a lifetime we might test 1,000 drugs. And we shall need to postulate a prevalence. We need to know how many of those drugs are active and how many are not active. Let's take as an example, because we're unlikely to know this number exactly, but let's suppose that the number of drugs that are active is 10% of all of them. That's probably quite optimistic given the low rate of success for drug discovery. So there's a real effect in 10% of the cases. If we do 1,000 tests, 100 of them will be on drugs that are active, and 900 will be on ones that are inactive. We now do a test of significance on all of these, and if we use a significance level of 0.05, not to be recommended but very common nonetheless, that means that 5% of these tests will be false positives and 95% will give the correct negative answer. So we have 45 false positives. But again, we can't tell what the false discovery rate is unless we look also at the other arm, because we need to know the total number of positive tests. So let's suppose that the power of our significance test is 0.8. That means you have an 80% chance of detecting effect when there is one. In these 100 tests, there is a true effect, and we'll detect that correctly in 80% of the cases, 80 true positive tests. We'll also have 20 false negative tests where we fail to detect an effect when it's there. So now we can go ahead, because we have 45 positive tests here, which are false positives, 80 positive tests there, which are true positives. So the total number of positive tests is 80 plus 45, and the false discovery rate, the proportion of false positives, is 45 over 45 plus 80, and that is not 5%, it is 36%. So there's a very good chance that when we observe a positive test, that it's a false positive one. Okay, so the tree diagram approach was very simple to understand, and it certainly shows that there's a problem. However, it doesn't show all the subtleties of the problem. There's another way to do it, which is quite appealing, because it mimics what you would quite likely do in real life. If you had two samples and you wanted to test whether their means were the same, you might do a t-test. You shouldn't, of course. You should do a randomization test, which has been around for years now. You can find out about that in my book, which you can download from dcscience.net for nothing. But let's stick with the t-test now, because that's still what people use very widely. And what we do is to generate, say, 16 observations in sample 1 using a random number generator. They come from a distribution which is known in this case to be Gaussian, and which has a known mean and standard deviation. You generate another 16 observations for sample 2, and you do a t-test on the results, and you repeat that 100,000 times with different random data each time. That sounds a lot of times, but the paper to which I refer at the end allows you to download a script in the R programming language which will do 100,000 t-tests for you in about 3 minutes in a modern machine, so this doesn't take very long. Each of the samples which you generate will generate a somewhat different mean, and let's start with the case where the null hypothesis is true, so both samples actually come from the same distribution. If we look at the 100,000 differences between means that we get, it's going to look like this. This is an actual example. On average, the difference between means will be close to 0, because that's the true difference between means. But of course it can, in individual experiments, be a good deal larger. It can be 0.5, 1, minus 0.5, minus 1, and so on. Each of those 100,000 t-tests will generate a p-value too, so we can look at the distribution of them. And the result at first sight is often a bit surprising to people. The distribution is entirely flat. A statistician would say that the distribution of p-values under the null hypothesis is uniform. It just means it's flat. Now, of these 100,000 p-values, we find that 5% of them here are below 0.05. This is the 5% of false positives you expect when there is in fact no effect. All the other p-values are bigger than 0.5, and the number of p-values that occurs between 0.6 and 0.65, for example, is just the same as the curve below 0.05. It's 5% of them. So there's no reason, at least it is the case, that if you repeat a t-test on random data, it's quite likely that the second time you do it, you'll get a different result from the first time. That's a separate problem from the one we're dealing with now, and it's dealt with in the paper briefly, but we won't talk about it further here. That's when the null hypothesis is true. We also, of course, need to repeat this for the case where the null hypothesis isn't true. We can do that by generating one sample which has, say, a mean of 0, and a second sample which has a mean of 1, so there is a real difference between them. And of course we find that the distribution of p-values will be different. If the power of the test was 0.8, there would be 80% of the values below 0.05, the rest above it. So what we find if we combine values from the case where the null hypothesis is true with ones where it isn't in the proportion dictated by the prevalence, we find that we get from this approach exactly the same answer as we get from the tree diagram. In the case where the prevalence of true results was 0.1, we would find that the false event rate came out to be 36%, just as we got from the tree diagram, if we look at all p-values less than 0.05. However, that is arguably not what we should be doing. The tree diagram that we've used and the t-tests example that we've mentioned both suppose that the prevalence of true effects in the over a lifetime of doing t-tests was 10%. Of course, the result you get for the false discovery rate is quite sensitive to that assumption, and if in the tree diagram we put in a prevalence of true effects of 50%, then we find that the false discovery rate comes out at only 6%, and then 6% is near as damn it 5%, the significance level that we use. So you might think in that case there really isn't a problem to make a fuss about. There's only two snags with that. The first is that there's not the slightest reason to think that the prevalence of true effects is 50%. That would be a very optimistic assumption. Clearly, under many circumstances, it's much less than that. But there's a more subtle reason why the tree diagram approach is not entirely realistic. And that is that it looks at all tests that give p equal to or less than 0.05, whereas we've observed just a single p-value. The aim of this exercise is to try to judge or try to interpret the meaning of the result if we do a single t-test and we get, say, p equals 0.047. We want to know what that means. So when you come to think about it, it seems in order to interpret that, we should look at the results of simulated t-tests, but we should look only at those results that gave p equals 0.047. That's what we've observed, and that's what we're trying to interpret. Now, what we've done so far is to look at all results that give you p equal to or less than 0.047. But why include the equal to or less than bit? Now, if you're doing the simulated t-test, it's very easy to mimic this process. We simply have our 100,000 p-values, and we look only at the tests that give you p equals 0.047. Well, p is a continuous variable, so we have to take a little interval. So we look only at the results from the 100,000 simulated t-tests that give p-values between, say, 0.045 and 0.05. And what the outcome of this will be is to show that there is a problem even in the most optimistic case. So the results are somewhat more pessimistic than you get from the tree diagram. Here's an example. Take the case where the prevalence of true effects in the population is 50%, because that in a sense is the most optimum case you can look at by the tree diagram approach. It gave only a 6% false discovery rate when you use a significance level of 0.05. If we look at that case in this new way, looking only at the p-values between 0.045 and 0.05, the false discovery rate comes out to be 26%. Rather surprisingly, to me at least, this is almost independent of the power of the test, of the sample size. So even in this best possible case, the false discovery rate is 26%. It's not 5%. If we repeat these tests, looking at the case we did in the tree diagram, where the prevalence of true effects in the population was only 10%, then we find that the false discovery rate in that case is a completely disastrous 76%. The odds are, in such a case, that there really is no effect at all, but chance when you use a significance level of 0.05. So there really are problems, regardless of what the prevalence. There's yet another little problem that arises from this exercise, which is very easy to determine by doing simulated t-tests, and that is that if you look at the tests that come out significant, if you do think you've detected an effect, then the effect size is going to be exaggerated. It's going to be truer than the big one. This is a lot of t-tests, was worked out from a lot of t-tests in the case where the true difference between means was actually 1.0. We test for the difference between means. For each difference between means that comes out as, quote, significant, unquote, we look at the size of the difference between means and we average that over a lot of results. And we would hope that the average effect size would be 1. Well, if you have very big samples, this is for 50 in each sample, so the power of the test is really quite high, then we do get an average effect size of 1. But it's very rare for tests to have a power as high as that. The best example we've dealt with was where there were 16 in each sample. That gave you a power of about 0.8, so the effect size is exaggerated by about 15% or so in that case. We've also mentioned, though, that it's very common for results in the literature to have a lower effect size, down to 0.2 or even less, and you can see that when that's the case, then we're going to have an average effect size which is almost twice the real effect size. So no doubt this contributes to the well-known phenomenon that the effect size for a treatment effect tends to decrease with time. There's a good statistical reason for that, is that as the number of observations accumulates, then the exaggeration, the effect size inflation gets smaller. There's also, of course, bad reasons for it, like with the passage of time, the number of brownie points you get by finding a big effect is reduced. So in this case, the leftmost point corresponds to a sample size of only 3, which gives you a power of only 15%. Right, so there are some of the problems. So the big problem now becomes, what do you do about all this if your aim is to not make a fool of yourself by claiming that there are effects when there are no such effects, by claiming that you've made a discovery when all you're seeing is chance? Well, the first thing to notice is that it's a fundamental assumption of all significance tests that treatments have been assigned at random. People don't seem remarkably unaware of this. The easiest way to see it is to look at the randomization test methods described, for example, in my textbook, available free from dcscience.net, but many other textbooks deal with them too. They show very clearly that it's a basic assumption of the test that we've made is that the treatments are allocated randomly to individuals. If that's not the case, then you can't expect the test to give a correct result, and it's like the situation is likely to be worse than it would be if the treatments had been allocated randomly. This means that any significance test applied to survey data, for example, is completely invalid, and what the results mean, well, it's really uninterpretable. But most lab experiments tend not to be randomized either, so it's not actually valid to apply significance tests to them. They may give you an idea, but they're likely to be over-optimistic. Okay, so the cases we've discussed here, which have disastrously high false discovery rates on the whole, were properly randomized, and let's suppose that's been done. So how do we then proceed? Well, the first thing that should be absolutely apparent is that you should never use the words significant or non-significant, and never ever use those pesky asterisks which are used to decorate so many graphs in the literature, because they're equivalent to using the words like this. Suppose you have two tests that gave p equals 0.04 and then another one that gives p equals 0.06. Those two tests mean essentially the same thing. It is an absolute nonsense to label one of them significant and the other one non-significant. That should be quite obvious. P varies continuously, and there is no magic cut-off point between that will tell you what's true and what isn't. So what do you do? Well, you state a p-value, not p is less than something. That's a hangover from the time when you had to use tables to determine p-values. You just give the exact value. And just as important, you then give an estimate of the effect size. That's what actually matters in the end. And you put confidence limits to that effect size. This is a nice visual way of telling you the result of an experiment with some idea of the uncertainty in the effect size estimate, but you have to be aware that doing this tells you absolutely nothing about what the false discovery rate is, and that's the aim of this paper, is to be shown that, is to show that under most circumstances the false discovery rate is a great deal higher than you think. So what do you do about that? You can compensate for it to some extent just by changing the wording. If you see p equals 0.04, you don't claim you've made a discovery. You say that it means that this result might be worth another look. If you want to ensure that you have a low false discovery rate, then you can do it roughly, but to quite a decent approximation, simply by not accepting p-values which are as big as 0.05. That gives you, as we've seen, an absolute minimum of 26% false discovery rate. If you use p equals 0.001 as your cutoff, then this will give you a false discovery rate which you can pretty much guarantee will be less than 2%, regardless of the prevalence. So that is safe. Of course, it would result in a very large number of discoveries vanishing from the literature. That, of course, might be no bad thing, because many of them do turn out to be false discoveries in the long run. That's what the irreproducibility crisis is about. We must point out, though, at this stage, that what your attitude in real life will be will depend not only on the things I've mentioned so far, it'll also depend on the cost of making an erroneous judgment. The cost of claiming a false discovery is largely a cost to your own reputation. So-and-so is always claiming things are true and they turn out not to be. It's not a very good reputation to have. And if you want to guard your reputation carefully, you won't take anything less than p equals 0.001 or so as your criterion. On the other hand, there may also be a cost in failing to detect a real effect when it's there. And if you use p equals 0.001, you're going to miss quite a lot of real effects that are actually there. If, for example, you're doing a preliminary screen on a series of drugs, it would be silly to use p as low as 0.001 because you're going to miss a lot of potential drugs. It would be perfectly reasonable in that case to use 0.05, but remember that all that's saying is that it's worth another look. At that stage you would have to go along and look in more detail at those candidates. No doubt some of them will turn out to be inactive, because that corresponds to quite a high false discovery rate, but at least you wouldn't miss many of the really active drugs. So the conclusion of this talk is that the greatest statistician of the 20th century, Ronald Fisher, probably had it wrong when it came to doing tests of significance. He really was a towering figure, both in theoretical statistics and experimental design. He didn't, in fact, mandate a p equals 0.05 cutoff level. That's a later invention that's been tagged on. But the whole business of null hypothesis testing, which was his approach, has turned out to be unsatisfactory. It gives you at least a false discovery rate of 26-30% if you use p equals 0.05 as a cutoff. So we have rather reluctantly to come to the conclusion that the physicist come journalist Robert Matthews was right when he said in 1998, the plain fact is that 70 years ago Ronald Fisher gave scientists a mathematical machine for turning baloney into breakthroughs and flukes into funding. It is time to pull the plug. We don't want more baloney. Thank you very much. You can read more about this on my blog. There's a simple version on the blog, which is where the work started. There's a part on if you put on hazards of significance testing in the search box, you can come up with part 1, which is about screening tests, and part 2, which is a simplified version of the p-value interpretation. It's been written up now as a proper paper published in Royal Society Open Science. It's a nice journal, takes papers in every field, and it's free at the moment and is totally open access, and it has comments. It is the future face of publishing, in other words. In fact, the paper was available for 4 months before it came out in the proper journal, because I'd posted it on the preprint server archive. That's only for physical and mathematical sciences. I posted it in the statistics section, but there are equivalents now for biology, which are very useful. And it sat there for 4 months, took 24 hours to appear, and I've been collecting post-publication peer reviews for those 4 months, which contributed to improving the final paper. It looks as though the journals, traditional journals, are no longer needed, and the sooner they go, the better.